All right, one more time, ladies and gentlemen. We have a powering AI infrastructure with innovations in reliable in-system on-die memory design and characterization starting here in about 1 minute. If you could make your way to the exhibit forum floor, we're going to be starting here in just about 1 minute.
So we just press the green one?
Yep. If you need to go back, just say out loud, can you go back one?
Okay. And is this on now?
Did you switch it up? Yep.
Hello? Welcome. Hello. All right, folks. We are Infosys. We are happy to be here for the first time ever. Welcome to this session where we're going to briefly tell you about Infosys' semiconductor engineering. So, Infosys is an $18 billion annual revenue company, a publicly listed company. Most of you know it as a very large software infrastructure and engineering services company. What you probably don't know is that Infosys is pretty big in semiconductor engineering as of the last 18 months through the acquisition of a company called InSemi in Bangalore, India. And that's the part that I'm going to focus on. And my partner, who is the founder of InSemi, he's going to tell you in particular how we are applying some pretty cool AI techniques to help several aspects of semiconductor engineering. So Infosys is what we have is a term called chip to cloud. So we have the ability to not only provide full cloud services today, but we have the ability to design components, which is the semiconductor components that go into the clouds today through all the systems that make up the customer base of Infosys. So what does that mean in terms of semiconductor engineering? It means we today pretty much do every single aspect of semiconductor design that you see any chip company do in the world today. So from RTL design to design verification to design for test, everything that's essential to chip design, Infosys does today. In addition, we do middleware development that'll enable these chips to act in systems that we provide support for also. So Infosys is not only now in the software business, it is now completely in every aspect of the technology business. If you look at, in terms of competency, what that means for semiconductors, every single key competency that you need in the industry, from RTL design to physical design to verification to design for test, these are all key competencies that any chip design company would require. We also have the ability to do custom designs. We have the ability to do memory standard cell, and I'll focus on this memory standard cell IOs, which we call in the industry foundation IP, more specifically in a couple of slides. And then, of course, the other stuff is FPGAs and embedded software design. So that is what we believe gives us the ability to really be what we call a fabless ASIC operation. We don't call ourselves a fabless ASIC company because we don't sell chips. We sell the services to do fabless ASIC. Now, with that said, why is that important? And so what's the big deal? Because the big deal is that where we're really focused today is in the area of data center chips, so high performance compute. And in high performance compute, there are three areas that are key core competencies that a lot of service companies will tell you they can do, but these three areas really distinguish us, I think, from other companies. The first is foundation IP design. What is foundation IP? Foundation IP, why is it important? For instance, on-chip SRAM. Today, more and more AI algorithms need a large amount of off-chip memories, and that translates into bigger caches on chip. To be able to design those caches and those standard cell elements in 2 nanometer technology, which is a completely new type of transistor than what you had in FinFET or before that, is a completely different core competency that only our people have. And I'll tell you why in a bit. The other part that's really important is testability design. So every chip that's done, it's done at a very high cost, mass cost, and it has to be very reliable in data centers for the lifetime of the device. To be able to test those devices before they go into manufacturing at a very sophisticated level is a very differentiated competency, and we have that. The third part is the power design of the systems. So we are in the practice of something called integrated voltage regulator designs, and I'll expand on that. Why is that important? Because every percentage of power you can save in the data center can translate into kilowatts to megawatts of power savings. First, in the area of foundation IP. So why is foundation IP important? Because every single AI chip needs bleeding edge processes. So you need the next generation of device to come in the latest process so that you can get the best power savings. That means the underlying foundation elements, you have to have the capability to do the designs in nanosheets, for instance, which not every company has. We have that because our founders of this semiconductor division come with this DNA of foundation IP. On-chip SRAM reliability is a key component of die area more and more. You know, if you look at the AMD Ryzen, it takes almost 60% of the die area is on-chip memory. So to be able to do that memory reliably is a key core competency. And then first-time right silicon depends on the dependability of these on-chip circuits. Another reason our team is really good at this is because we engage with 0.1 of the PDK with the foundry. From the time the foundry starts the process, we engage from that standpoint all the way to production. Very few companies have access to that type of foundry technology. And even at the latest nodes, we are engaged at those levels. And the other reason, and we're going to expand, my partner is going to tell you about why we have this differentiated capability in foundation IP, which is that we have techniques now to do very large amounts of memory designs, for instance, using accelerated AI techniques, which allow us to rapidly validate and do rapid instantiations of multiple memories in multiple chips, in multiple types of processes. The other key thing about AI is that you need to be able to provide sophisticated levels of testability. So why? Because if you look at the typical SoC failure trends over time, uh, aging and wear-out failures are a key part of failures that every SoC has. And to be able to detect those and be able to eliminate those early in the cycle is a key element of device reliability. And our ability to do BIST, for instance, built-in self-test, is a key enabler of that. Our also ability to do, for instance, built-in self-repair is a key element in that. We actually not only do design service in this respect, we have the ability to have an embedded logic that we can put on a chip that can actually eliminate a lot of these reasons why you have increased testability is important for device dependability. The last thing that's very key to AI chips and their design is what we call integrated power delivery. So if you look at a typical current path in a typical conventional SoC or GPU that's designed for today's systems, they have a separate PMIC surrounded by a lot of inductors and capacitors that are separated by a little bit of PC board trace. Just this little bit of impedance can, by eliminating that, you can actually represent significant amounts of power savings in any system. And that's part of what's called integrated voltage power delivery. So if you look at one of the things TSMC shows that in their latest offerings of packaging, in the CoWoS packaging, you can actually co-package the PMIC with the SoC and surrounded with embedded deep trench capacitors so that you significantly reduce the power that's lost in the traditional PMIC to SoC path. And this in itself can represent as much as 10 to 15% of power savings. In a data center, that can be up to 15% of power, 15 megawatts, 10 to 15 megawatts of power savings in typical data center, by the way. So these three areas, foundation IP, design for test, as well as integrated power delivery, are key areas, are the ways we are helping AI chips become being designed quickly and being designed for durability. So with that said, let me hand it off to my partner who's going to talk more about some of the design techniques.
Yeah. Hi, everybody. Just wanted to quickly talk about our innovation on the AI front for SRAM characterization. And quickly here, as you know, some of the challenges that we face in SRAM design, that has not changed from a long time. The complexity with the growing nature of network elements, the PVT variations, and then when you actually try to do cut variations, right, and localized basically on-chip variations that come into picture. So this makes your design, basically the design challenges of what we face. So if you look at the traditional ways how we do these memories, right, like either you take the critical path type of modeling or the corner variations. So these, by nature, have some of the limitations. Basically, you need to, you kind of do the regular worst case delay path analysis and then try to do a RC path in the critical path approach. The biggest problem for you is the accuracy is limited by how you actually do the modeling of these things. Or if you go to the corner point simulations, where you have some of the cuts for basically, the entire range of your memory, then the biggest problem what you have is these are large simulations that you have to do for the bigger, long, on the corners that are on the other side of the spectrum, And these actually give you a lot of inaccuracies because there is so much of interpolation that need to be done. So what we are trying to see is like what is a different approach where we can actually save the time and get rid of the inaccuracies that are there in the design. So let's say one of the ways we actually take a design, like in this case we are going to take memory as a design. So first thing what we do here is basically try to identify the leaf cells that constitute one of the memories. And like you say, like you see, generally we have the control block, the X decoder block, the array, and the IOs. I have just simplified this for for the presentation over here. So basically, once the leaf cells are identified, then we actually do simulations of these leaf cells through basically take the full parasitic netlist of these and run an entire basically a comprehensive simulations on this. Then we create a data set that actually becomes our trained ML model. Basically, we use this to create a complete training model. And then after this, so this is an extensive thing where we use our regular licenses. But the only thing is, because we are actually doing it on a very small leaf cell based simulations, right? So we don't have we don't have to use the timing that is required to do these simulations are much smaller. Then we actually use this second part of the simulation where if you want a particular PVT or a cut, then once you give this to our ML model, it actually generates a predictive model of all your characteristics. Basically, this will then create a complete synthesis of your end-to-end results. So that's the thing that we are actually developing and we have developed. And if you look at it, the very first part, the phase 1, is something that where you do an entire spice level simulation of all the leaf cells and use that for the learning of your models. And this is very, it's a one-time, and there is need of licenses and all of that. But anything beyond in your phase 2, where you are actually doing it on your, on the entire netlist, right? It is just a prediction based on synthesis and PVT cuts and corners. So this is something that we have developed, and this is the model. Again, here we are just still doing a very linear regression type of models, and we are developing the model on this. This is something that we are proprietary kind of thing that we are developing. But this is where we do, we think what we can do out of this is, basically accuracy-wise, because we are going to be taking complete end-to-end, taking all the leaf cells and simulating them. And because all the parasitics are accounted and prediction of each corner will be accurate. And then since the spice is only used in the initial phase, and in the second phase there is no spice at all, so that actually reduces quite a bit of reduction in runtime, which I think is one of the biggest challenges when we have larger instances. And basically, because we are doing the simulations at the leaf cell level, the statistical timing and the local variation can be added to each of these to manage the variation aspect as well. And so everything is automatic after that. So basically, there is no manual intervention. So it can automatically take your worst case path and find out what is the, what is the worst case delay in there. So there is that also we think is a benefit out of this. And basically, the whole thing can be, scalable with the use of AI in this particular case. So right now we have used the gradient boosted GBDT model for this, and we are actually working on the extreme boost regression mode. The 5 features that we have basically tried to use are the process, voltage, temperature, input and the output slew for each of the leaf cells. And we have looked at the cell delay basically, and RC delay for all the, and these are the ones that are stitched to get our final output. And this basically data set that we have used is about 165K. And this is the heat map based on different temperature, PVDD, slew, and process, and how how each of them correlation heat map is here. And just for this case, we used a 64x4 cross CM2, and basically the 4 leaf cell blocks and the data set generation. And this is basically the error, MAPE error, and the root mean square error that we have got for these data sets. So these are the results that we have from the actual values to how the predicted values are. Again, like I was talking about, we just used a simple regression model here. We were trying to, we are trying to work with a model that is actually suitable for our memory. It's going to probably take a few more cycles to do that. And once we do that, I think we will have, the good thing about it is because it is IO is like the leaf cell level, we have a complete control of each of these blocks, and it's fully parasitics are taken into account. The the accuracy will not become a major issue here. So this is the accuracy part that I was talking about. So basically, from a predicted versus actual, given the time that we take to do these things, I think we can get to almost like a 5% error, error rate, which is okay for most of the initial guesstimate that we are going to make. So some of the runtime biggest gain here, what we have tried to achieve is basically the runtime and using of these licenses, which is one of the biggest challenges. And from a corner point analysis, we have a reduction of about 90%. And compared to like runtime wise, we have, if you do a critical path analysis, then it's about 55% improvement in time. And this is the time that is approximately taken for the instance. If I, basically for the leaf cells and going through all and making sure I complete, I do a complete data set for that. And then if I'm going to do one cut, then it's going to take about 30 minutes. And anything after that to evaluate an access time for one cut, one PVT corner, it's about 20 minutes. So I think what we can see is, compared to the existing methods, this one, we tend to save significant amount of runtime, and which is one of the biggest challenges that we have. And basically, if there is any change that we have to do once the design is done, I think this this particular method, because we are trying to run most of these extensive simulations on the leaf cell, this actually helps us develop an entire memory and you don't have to go through the entire worst case analysis or a critical path analysis. So what we are trying to do, like I was talking about, we are trying to come up with some neural network-based and tree-based networks to get higher accuracy. Right now, we are not there yet, but like I said, it was just a linear regression type of model approach. And we are also working on other PPA metrics. So we have similar things that we are working on power. There is another track where we are doing the setup and hold time analysis on the same thing. And we need to do a lot of other things like NBTI, PBTI to be included in this and try to get the PPA analysis done on this. So that was the quick presentation that I had, and would love to see if there are any questions that. Okay, thank you.